Let's talk about the effects of fully loading a transformer. Now, we'll get into the reason why it's so important to understand that because it's going to eventually lead to a multi-tap transformer and why you have additional taps on transformers. So right now we have a transformer that is 1200 to 120 volts, which means it has a turns ratio of 10 to 1. And on this side, we have a supply voltage of 1200 volts. There's a difference between our supply voltage and what we call our terminal voltage primary and our terminal voltage secondary. So right now, what we have is an open circuit on the secondary, which means we have no current flowing in the secondary. We have that open there. If there's no current flowing in the secondary, there's very minimal current flowing on the primary to the point where we call it negligible because it's exciting current or magnetizing, which is just basically 2% of what the rated primary current is. So we're just going to call that negligible at this point. So in this situation, we're going to trace through and see what happens to our voltage. With no current flowing in the secondary, we have a supply voltage of 1200. Basically means we're going to get terminal voltage of 1200 volts on our primary. That's going to change once we fully load this thing. But right now, 1200 volts supply, 1200 volts terminal, 1200 divided by the 10 to 1 ratio will give me my secondary voltage, which in this case is obviously going to be 120 because it's a 10 to 1 ratio. Now we're going to close this switch, and that's when things are going to start getting a little crazy. We're going to say that this load will cause maximum current to flow in the secondary. If we want to figure out what maximum current is, we could just figure out that take 360,000 divided by 120 volts, and that will be that it is that rated current. So at this point, we do that, and we end up with a current of 3,000 amps. So we have 3,000 amps flowing in the secondary at this point. Now remember, when we talk about transformers, our primary is the source of voltage for the secondary. Our secondary is the source of current for the primary. So we can take that 10 to 1 ratio and we can take 3,000 amps divided by 10 to get the current on this side, or we could take 360,000 divided by 1200 volts to get our current on the primary. Either way works. 300 amps. We have 300 amps flowing in the primary because we have 3,000 amps flowing in the secondary. Now, there's a big difference that's going to happen here with our terminal voltage. Because we have 300 amps here and because we have winding resistance, you notice I've got that drawn here. This is the resistance of the windings or the line leading to it, and it's small. It's only 2.25 ohms on each leg, but still it is a considerable issue because when we have 300 amps, we're going to get a volt drop on that line and a volt drop on that line. So we're going to see that our voltage is going to drop by the time we get to the primary side. Using Ohm's law, 300 amps times 0.25 ohms gets me 75 volts on that line. 300 amps times 0.25 ohms gives me 75 volt drop on the line on that side. So in total, I have 75 plus 75. I have a 105 volt drop on the lines before it even gets to the winding itself. So we're going to take that 1200 volts minus the 150 is going to give us our new terminal voltage, which in this case works out to be 1050 volts, which is substantially smaller than 1200 volts. And you're going to see it makes a big difference on our secondary as well, because if we have 1050 volts here, then we've got divided by 10, because our turns ratio haven't changed at all, we're going to end up with a different voltage on this side. We expect 120, but we're actually going to get 105 volts, which could be an issue. So what we need to do is figure a way to increase the voltage on this side. And the way we could do that is by increasing our volts per turn on the secondary side, which is going to lead us into how multi-tap transformers work, which we will cover in another video.